Number 35. Suppose that with probability p, the random variable x has a normal distribution with mean 0 and variance 1, and with probability 1 minus p, x has a normal distribution with mean 1 and variance 1. What is the variance of x? Problem number 35. We're given that x is x1 with probability p and x2 with probability 1 minus p, where x is normal 0, 1 and x2 is normal 1, 1. And we're asked to find the variance of x. So first let's find the expected value, which is, you take it into this expression here, so that p is a constant, so it expects value x1, which is 0. And this is a constant, so the expected value of x2, which is the mean, so it's 1. So it simplifies to this. Now to find the variance, we also need the expected value of x squared. So we do a similar approach here. The p comes out, expected value of x1 squared. Now, there's a formula that says the variance of x1 squared plus the expected value of x1 quantity squared is this expectation. It's sort of the reverse of the variance. So we know the variance is expected value of x squared minus expected value of x quantity squared. So if you take this piece to the other side, then you given x squared. So that's what we do here. And then variance is 1, mean is 0, variance is 1, mean is 0, square them, it reduces to this. So now we can find the variance of x. It was the expected value of x squared, which is this, minus the mean squared. Reduce, 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 we get 1 plus p times 1 minus p. Number 36. Let x1, x2, and x3 be a random sample from the uniform distribution on the interval 0 to 1. What is the probability that the median is less than 0.4? Number 36, we have a random sample of 3. And we want to find the probability mean is less than 0.4. Now we're going to do this two different ways. We'll use the order statistic method, which again I highly recommend that you understand how to find the density of an order statistic. Once you learn it, then it's straightforward and it's hard to forget, but you have to go through the struggle of learning it. So here we want to find the median, which is the middle value, so y2 of a sample of 3. So this is the joint or the density for the second order statistic, which boils down to 6x times 1 minus x. So to find the probability that we are less than 0.4, you just integrate this function from 0 to 0.4. Integral, plug in the values, we get 44 over 125. Now the second approach is this. So how can the median be less than 0.4? And the median is our middle value. So if all 3 observations are less than 0.4, so the x1, x2, and x3, or 2 of the 3 values are less than 0.4. Well, we have 3 values and we want to choose 2 of them, so there's 3 choose 2, and then we just, each of those events are the same, so we can, it's a multiplier of the probability of one of those events. So one of them is less than 0.4, another one is less than 0.4, and another one is greater than 0.4. So since those are independent events, this is just 0.4 cubed, 3 choose 2 is 3. This first one, 2 of them being less than 0.4 is 0.4 squared, and then being greater is 0.6. That is 8 over 125. This comes to this and ends up being the same number. Number 37. let x and y be independent normal variables such that the mean and the variance of x are 2 and 4 respectively, while the mean and variance of y are 6 and v respectively. A sample size of 4 is taken from the x distribution and a sample of size 9 is taken from the y distribution if the probability that y bar minus x bar is greater than 8 is equal to 0.0228, then v equals, so number 37, we're given x is normal 2 with the variance 4, mean 2, variance 4. Y is mean 6, variance v. Sample size of x is 4, sample size of y is 9. And we're asked to find this probability that y bar minus x bar is greater than 8. But this linear combination of normal random variables is normal. So to find the mean of that linear combination, we plug it in, we get 4. And then the variance is just the sum of the variances. So it's v over 9 plus 4 over 4. Remember, these are not individual x's, but an x bar. So it's the average. So you have to divide by the sample sizes. So when we're here, if we subtract the mean and divide by the standard deviations, we ended up with the z variable. So we subtracted the mean divided by the standard deviations, and it's saying that that value is 0.0228. Well, if you look at a z table being greater than some value equal to 0.228, that implies that this number is 2. So when you equate those and you solve for v, you get v is equal to 27. Number 38, let x, y, and z be independent uniform variables on the interval 0 to a. Let w equal the minimum of x, y, and z. What is the expected value of 1 minus w divided by a quantity squared? So number 38, we have 3 independent uniform random variables on an interval from 0 to a, and let w be the minimum. We want to find the expected value of 1 minus w over a quantity squared. So each xi is uniform. So the cumulative distribution function is x over a. And then this is the density of the minimum. Again, this is an order statistic. And so once you appreciate how to find that, then it's pretty straightforward. And maybe I'll have a separate video on that later. So now we want to find the expected value of this quantity. Now I'm using x instead of w, but it's that we're over the density of w. So that means plug in this value, which is here, times the density, which is there. Well, that and this piece are the same, so they combine to 4 to the 4th power. We do a u substitution. We let u equal this center piece, and du is equal to minus 1 over a dx. So plug it in. And then the limits of integration are from 1 to 0. So that negative can actually be taken into the integral sign to change the integration. And not needed, but I kind of prefer it this way. So you take the integral, so that's 3/5 u to the 5th, plug in our limits, and we get 3/5 as the answer. Number 39, suppose x is a random variable with density f of x equal to 0 when it's less than 0 and theta e to the minus theta x when x is positive. And the probability that x is less than or equal to 1 is equal to the probability that x is greater than 1. What is the mean of x? So number 39, we have a density, and then we're given the two probabilities, being less than or equal to 1 is equal to being greater than 1. So let's find the probability of being less than or equal to 1. And so we integrate from 0 to 1 of the density, make a u substitution, We get this. Integrate that, or take the antiderivative. We get this, and I brought it back to the x world, not the u. Plug in the values, you get 1 minus e to the theta. Now, the thing that you realize, the two probabilities, those regions are independent and mutually exclusive. Or I probably should just say mutually exclusive and exhaustive. So they have to add to 1. So since they each equal 0.5. So this probability is equal to 0.5. So you set them equal, which implies, you start solving for theta, you get theta equal to log 2. Now we want to find the expected value of x. Okay, so I did this 2 approaches, and I'll explain it in a second. I'm only going to show you one, but I'll explain what I did for the second one. So the expected value, you put in x, and then it's times the density, which was what we have here. The theta is constant, bring it out. Now you recognize that this is a gamma density. So 2 minus 1 is just 1, so that's the x. And then we have minus x over, and if you take this theta down to the denominator, it's theta to the minus 1. And so that integrates to gamma of 2 times theta to the minus 1 raised to the 2, which is alpha. So this simplifies to 1 over theta, which is 1 divided by log 2. Now in this integral here, you don't have to sort of manipulate it to make it look like a gamma. You could use integration by parts and you'll come up with the same solution. So the second approach that I tried, which is I plugged in log 2 for theta. And now the log and the e kind of cancel and it simplifies a little bit, but you still have to end up doing integration by parts. It's kind of a fun exercise to go through, but really there's no benefit added by showing that solution. So the final answer is 1 over log 2. Number 40, let x1 through x5 be a random sample of size 5 from the uniform distribution on the interval 0 to theta, where theta is unknown. Let the estimator for theta be k times x max, where k is some constant and x is the largest observation. In order for k times x max to be an unbiased estimator, the constant k must equal. Problem 40, we're given that x1 through x5 are uniform 0 to theta. So here's the density, here's the cumulative distribution function, and we want to know the value of k such that makes k times the maximum of our sample to be an unbiased estimator for theta. So the 5th order statistic, or the largest, the maximum, the density is this using order statistics theory. And then we want to find the expected value of k times x. So you plug in kx times this density, and then you bring out the constants. So you have x to the 5th dx, integrate that, take the antiderivative, plug in the values, you get this. So the value of k that makes this theta, because that's what we want left over, is k equals 6/5. Number 41, let x1 through xn be independent, each with an exponential distribution with density function equal to lambda e to the minus lambda x, and x is positive. What is the distribution of y equal 2 times lambda times the sum of the xi? Problem 41, we have a sample size of n, and we're given that it's an exponential distribution, and we want to find y, which is equal to 2 lambda times the sum of the xi from 1 to n. Okay, so here's one note. If we let z be chi-squared r. Okay, so what's above the pointer is interest. Now below is different, and I'll show you in a second. If z is a chi-squared with r degrees of freedom, this is the density. Okay, so we'll need this relationship in a second. So now, and again, the top is not necessarily related to the bottom. So if we let y, we're going to look at one case first, so 1i. It asks us to find the sum, 2 lambda times the sum of all these xi's. But let's just use 1. So then we solve for x and we find the derivative of 1 over lambda. So the density of y, which is one of those x's, is equal to the density of x with this x plugged in times absolute value of the Jacobian. And so we get this. And it reduces to this quantity here. Now this is a chi-squared with 2 degrees of freedom. And you'll have to make that right in your mind. So that's 2 degrees of freedom. So now, and that was for one x. So now if we want to sum n of those x's, and the sum of chi-squareds is chi-squareds where you just add the degrees of freedom. So we're adding n chi-squared 2 degrees of freedom. So the answer is that this distribution is chi-squared with 2n. Number 42. Suppose that x1 through x2 through ... are independent random variables, each with probability of success p and probability failure 1 minus p, where p is between 0 and 1. Let n be the number of observations needed to obtain the first success. What is a maximum likelihood estimator of p? Now, number 42, it says that we're going to continue a trial until we find a success. And the success probability is p and failure is 1 minus p. And we want to know the probability that we end on the nth case. That means we have to have n minus 1 failures and the last one be a success. So this is the density. And we're asked to find the maximum likelihood estimator of p, the probability of a success. So let's take the partial of f with respect to p. Now this is a product, so we take the derivative of the first times the second plus the first times the derivative of the second. We set it equal to 0 and we solve for p. So here I factor out an n minus 2 in both terms. We're left with this and this. So we have two numbers equal to 0. So one or both of them have to be 0. So if we set this one to 0, it implies that p is equal to 1. And that's one possibility, but we're not going to examine that. No, actually it can't be, because we want some failures in there. The probability of failure would be 0. So this doesn't really make sense. So we set this equal to 0, and it falls out that n times p is 1, which implies p is equal to 1 over n, and that's the maximum likelihood estimator of p.